Recording in progress.
Okay, so today we're going to start chapter 20, which is derivatives of carboxylic acids. So this is kind of a continuation of the aldehyde and ketone chemistry, but we're going to change up one side of the, or one half of the functional group. Well, so the general form for the stuff we're going to talk about is like that, where we still have our carbonyl, and we have where R is a carbon chain of some sort, but in this case, Z is a heteroatom of some kind. So we're only going to talk about oxygen and nitrogen and halogens. But another thing to notice about the central carbon here is it's got 1, 2, 3 bonds to heteroatoms and 1 bond to carbon. And so there's one derivative we're going to talk about that doesn't look like this if you have a carbonyl, but it's sort of related to all the other ones. Okay, so from most reactive to least reactive. Here's the ones that we're going to discuss. If Z is X, a halogen, then we have an acid halide or an acyl halide. There's this interesting structure, which looks like carboxylic acid bit attached to another carboxylic acid bit. This is an acid anhydride, or just an anhydride. The reason for that is it's essentially 2 carboxylic acids minus water. So anhydride, put them together, you get this. Carboxylic acid itself. We have this one. Do you remember what that one is? An ester. And then similar to esters, are anids, just like an ester, but with nitrogen instead. And then final one we'll talk about looks significantly different from all the others. And that's because it doesn't have a carbonyl, but instead it's a carbon-nitrogen triple bond. Has a lot of the same characteristics. It's electrophilic at the carbon. But that's a nitrile, which is an organic cyanide. But fortunately, they generally aren't very toxic cyanides. Okay, we're going to go through these in order. And so We're not gonna immediately talk about the parent, the carboxylic acid. We're gonna start with the most reactive ones because let's say you've got two of these functional groups in your molecule. The ones that are toward the left are gonna react first. Yeah.
Are those labeled most least reactive? Like in order?
Yes, in order. Yep. Okay. Acid halides or acyl halides, call them. What I'm gonna do for basically each of these is we'll have a little mini section for each of the functional groups. And I'm gonna talk about how you make each one and then what reactions they do to make other functional groups. So there's gonna be several places where I'm gonna do like basically start repeating myself. And it's not because I forgot what I already said, although that may be the case. But like there's a way to get from carboxylic acid to an acid halide, and there's a way to go from an acid halide to a carboxylic acid. And so we're going to talk about that reaction right now, but twice in this chapter, just so you can see the different directions you can go with these things. Okay. Okay, so how do we make acid halides? There's basically one reaction here. We start with carboxylic acid. And treat it with SOCl2. Which is thionyl chloride. Pretty nasty stuff. But acid halides are really reactive, and so we have to use a really strong reagent to make them. All of the acid halides I'm going to talk about are acid chlorides because they're by far the most common. You can make acid bromides if you want, but nobody really ever does that. So we're just going to stick with chlorine in this case. And you also get SO2 and HCl as side process. Okay. Reactions of acid halides. The most common one and also the most annoying one is hydrolysis. As I said, they're very reactive, and so they'll react with water. If you don't even need acid or base or any sort of catalyst or anything, they just spontaneously react with water. Well, and that gives you the acid back and hydrochloric acid, but a lot of times this just bubbles out as hydrogen chloride gas. Okay, so this is generally pretty annoying because we've just gone through all this business to make our reactive acid halide, and now if we let it get wet, it's just destroyed. But we can say, okay, instead of water, why don't we use an alcohol? And then we can actually do some chemistry and not end up with a carboxylic acid. So if hydrolysis is for water, then use an alcohol. Alcoholysis. And take our acid halide. Add an alcohol. And then, like in this reaction, we're going to make HCl. And so we need something to kind of mop that up and sequester it, I guess. And for that, we're going to use purine. And the result of this is not a carboxylic acid. Instead of the hydrogen there, we get an ester with the R group on the alcohol attached. So now we've actually made a useful kind of functional group here. So as an example, we take acetyl chloride and react it with this benzyl alcohol with pyridine. What do we get? Well, we know we're going to have an ester here instead of our acid halide. And the R group on the ester is going to be whatever was attached to the alcohol. So that's just going to be this whole organic group here. So there's the start of our ester, and the R group is that. What?
Does that make sense?
Okay, good. A lot of lysis words today. M analysis. Okay, so we're going to take our acid halide, and we need two equivalents of an amine of some kind. I'm just going to use ammonia here as a simplified example. But this is just going to convert our acid chloride to amide. And we get ammonium chloride as a byproduct. The reason we need two equivalents of ammonia is because we've got one nitrogen here, and this other nitrogen just sort of takes up the hydrochloric acid. Because this is ammonia plus HCl. So from acid halides, we can at least go to carboxylic acid, not a particularly useful transformation, but alcoholysis, that's really useful because we can make an ester and we can also make an amide. Common trend in this chapter is you can treat a lot of things with Grignard reagents because all of these sort of different functional groups have carbonyls, and Grignard reagents like carbonyls. Okay, so if we do a Grignard reaction on this acid chloride, this is generally been overkill because you have to go through this sort of high energy process with really strong reagents to get to the acid halide, and then you're going to react it with a greener reagent. Well, you could have just done a greener with this or with this. So this particular reaction isn't commonly done, but in principle, it's just as good as any of the others. The main thing here is that instead of like with a ketone, where you get one of the new R groups from the green reagent added, here you get two. So always adds two equivalents of green green. That can be good, or more often is a problem, because a lot of times you're going to add one, and that's not going to work. Okay, so there's acid halides. On those. Doing a lot of general, it's a lot of R groups here, and we're going to continue doing that. And then sort of toward the end, we'll do some examples where we have all sorts of different functional groups on actual molecules. Okay, anhydrides, which that. There's, so technically, to make one of these, you could take just a regular carboxylic acid, heat it up super hot, and it will dehydrate and give you an acid anhydride. But in practice, that's not really going to work for any sort of significantly sized molecule that we might be interested in making. And so generally, you're going to have to start from an acid halide. Yeah, this is why we're doing them in order of reactivity, because generally speaking, you're going to use a more reactive compound to make a less reactive compound. Okay, and it's down a little bit. Okay, now what we need is we've got sort of the left side of the molecule, but we need the right side. And the right side is going to come from a carboxylate ion, which is just carboxylic acid that's been deprotonated by treating it with sodium hydroxide or something like that. And you just put these two molecules together. And we get our acid anhydride. The advantage of this reaction here is, well, I told you this is sort of like eliminating water from two carboxylic acids. And but here we aren't doing that in the reaction. The reagents that we've already prepared don't have that extra equivalent of water, but regardless. So acid anhydrides within molecules that are more complex are not quite as common as the parent anhydride, which is acetic anhydride. And that is most common for a reaction called acylation. So that's acetic anhydride. It's certainly the most common acid anhydride. Have you all used this in lab? Yeah, didn't we use it at the beginning?
Yes.
Yeah. It's horrible. It's like, well, acetic acid is like vinegar's older brother. Acetic anhydride is like the abusive dad. Okay, so if we take this and we treat it with an alcohol, which I'm pretty sure is what we did. Oh yeah, I'm gonna give you an example. Then we get an ester. Sort of a common theme here. We're taking a reactive carboxylic acid derivative, adding some organic molecule to it, and we end up adding it onto the end of the. You can also do the same, but with an amine of some sort. You could use ammonia here, but this works best if you add some substituted amine, and we get substituted amide. So we still have our nitrogen next to the carbonyl. If it wasn't substituted, it would be an NH2, but we have an NH and then an R group. That's valid as well. And the classic example of this is the synthesis of aspirin. So here's salicylic acid. Acetic anhydride we often abbreviate as AC2O. So not actually AC. So if we say that acyl group is AC, then there's just an oxygen with two of those groups on it. So that's our abbreviation for acetic anhydride. And all right, so we take the we take this group and add alcohol, the R group of the alcohol onto the end of the ester. So what I'm showing here is we're starting with the alcohol. Carboxylic acid is not going to react in this case because we have an alcohol instead. And so this is our R group here. Oxygen, there's our oxygen, and then just the C. So. and that's your aspirin acetyl salicylic acid. It's got an acetyl. So now we're going to talk about actual carboxylic acids from the parent group here. And we'll do a little more detail on nomenclature and then specific properties of carboxylic acids because they're important. So for nomenclature, the suffix that we add is oleic acid, benzoic acid, etc. So if we have this carboxylic acid with a parent chain of 4, so the parent chain is butane, and so we get butanoic acid. This one has a common name, butyric acid. Kind of sounds the same. Don't remember exactly where it comes from. This one's particularly stinky. This is the smell of vomit.
Ew.
Yeah.
Wait,
go-
in our vomit?
Like, yes, it is.
Oh,
Yeah, fantastic. So some more, less horrible, but the common acids. This one, I mean, I said that we have to have an R group here for carboxylic acid, but this is an exception. Formic acid. Does anyone know the sorry. I forget my taxonomy stuff, but it's like either a group or a family or something. It's Formica. I know a piece of biology trivia that biologists don't know. Yay! That's ants. This is what makes ant bites sting. And so that's where the form name comes from. So formaldehyde, because it has just one carbon, that's where the name. So it all actually comes from ants.
wait, you said N-file state.
I mean, they do, I guess. I've never like smelled one because it stinks. But this is what makes ant bites sting.
Oh, sting.
Sting, yes.
Ah, I'm sorry.
Sting, whatever. Shoot. All right, this one, we should all know this one. Come on. Well, yeah. Acetic acid, just vinegar. And then. It's Monday, we're all waking up, so. Benzoic acid, sodium benzoate, which is that with a minus charge in the sodium atom, is probably the most common food preservative, other than just salt. Acid. Sodium benzoate preservative.
Oh,
Yeah, it says
my favorite part.
okay. Okay, so I mean, obviously, we already know what the structure looks like, but one particularly interesting result of the structure is that if we have one carboxylic acid molecule sitting like this, and we have another one like that, then we get hydrogen bonding between the carbonyl oxygen and the acidic hydrogen. And so what that ends up meaning is if we take acetic acid, 2 carbons, carboxylic acid versus ethanol, 2 carbons, then alcohol. Boiling point of ethanol is 78. So based on that hydrogen bonding, what do you think the boiling point of acetic acid would be? Higher or lower? Higher. In fact, significantly higher, 118. So yes, we're increasing the mass of the molecule a little bit by adding the extra oxygen versus the 2 hydrogens that are here. But the main factor is we've got this really strong hydrogen bonding. And in order to get the acetic acid to boil, you have to put enough energy into the flask or whatever to break those hydrogen bonds. Okay, probably the more important part is, well, there's the carboxylic acid, so we would expect it to be acidic. So I know I haven't really drawn it explicitly yet, but I'll do that now. And that is carboxylic acid actually doing its acidy stuff, which might include being deprotonated by a base of some sort. So our hydroxide goes for that acidic proton. Talk about why it's acidic a bit. And the OH bond goes onto the oxygen atom. So now we get a salt. So this is our carboxylate ion. And this compound is from acetic acid, sodium acetate. Okay, so why are carboxylic acids acidic? I've run that process, and that's fantastic, but can't we do the same thing with ethanol? Right, we've just messed with the OH here. So we can do that same thing for ethanol, right? Okay, nice. So ethanol is acidic too, right? Sure. But key part here is that this molecule has no sort of resonance stabilization. It barely has any inductive stabilization. It's just this negative charge hanging out there on the oxygen with nothing to do. Now, that makes this an excellent reagent for SN2 reactions and all sorts of other stuff, but it doesn't make it particularly acidic. And in fact, just hydroxide is not adequate to deprotonate it, so that reaction doesn't even happen. You need something stronger. Okay, so that doesn't work for ethanol. Why does it work for acetic acid? Well, when we add base, remove that proton, we get initially this. Okay. Well, we can draw a resonance structure of this, where we move a pair of electrons to make a CO double bond, and at the same time, we break that CO double bond and move those electrons up onto the other oxygen. So we get that resonance structure. Now you might say, okay, well, if I just take this and flip it over, it's the same molecule. Got a methyl group, a central carbon with two single bonds and a double bond, a single bonded oxygen with a negative charge, and a double bonded oxygen is neutral. Same molecule. But these are still resonance structures. And so sort of an average resonance structure for carboxylic acid looks like that, where you've got sort of double bond character on both of these carbon oxygen bonds. And there's overall a negative charge in this area, but it's sometimes it's on this atom, sometimes it's on this atom. Never thought I'd write the words acid is acidic. But, okay, so it's resonance stabilized. So that means this is lower in energy, it's more stable. And so that means that this is totally fine to give up that proton if it gets it to a low energy state, lowish energy state, like that. Okay. So what would you rather still on your hand, acetic acid or sulfuric acid? Acetic acid, okay. So most acidic kinds of acids are sort of inorganic mineral acids like HCl, sulfuric acid, nitric acid, et cetera, et cetera. Sort of the standard ones that you use in general chemistry. The sort of least acidic compounds are most organic stuff. So obviously, like alkanes have essentially no acidity at all, but then alcohols are not particularly acidic. Ketones have a tiny bit of acidity on the alpha position, which we're going to learn about in the next chapter. But most organic compounds, or we don't think of them as being very acidic. Carboxylic acids. Acids are right here in the middle. So if you use pKa as a measure of acidity, which you may or may not have done organic one, I don't know, but the pKa of ethanol is 15 or 16. Carboxylic acids, 4 to 5. And sulfuric acid is 0. Many other acids are even more acidic. Sulfuric acid. So, and this is a log scale. So this is, carboxylic acids are 1,000 to 10,000 times weaker than sulfuric acid or these other acids. I don't know what 11 orders of magnitude is. Bazillions. That's a real scientific number. Ethanol is way less acidic than a carboxylic acid. So big jumps in between these, but I just want you to get the picture that carboxylic acids are a lot more acidic than most stuff that's going to be in the flask, but they're not significantly acidic compared to inorganics. Questions? Lots of reactions. All right, I'll see you in lab on Wednesday. Unless you're one of those people who's to see in both places. Yeah.
I don't know. Well,